start by saying that everything I talk about today, or almost everything that I talk about today, will be has come out of conversations that I've had with Darryl Funk, who was at Douglas College in Vancouver, and Mike Newman, who was at the University of Ottawa, and Jeff Whittle, who is my colleague in New Zealand. And I'm going to be talking about the mathematics that's sort of in the intersection of this Venn diagram. So it's at the intersection of the study of computing machines. So machines that compute things, what are they capable of computing, what are they incapable of computing, and the study of formal logical languages, what are they capable of expressing, what are they incapable of expressing, and the study of discrete objects, discrete mathematical objects, and the structure of those objects. So the structure of graphs, the structure of matroids, the structure of hypergraphs. And I'll be trying to look at this intersection through three different lenses. So I'm going to talk about complexity theory, so that's problems that are computationally tractable, problems that are computationally intractable. Decidability, which asks the question, when is there such a thing as a theorem testing machine? And also descriptive complexity, which talks about the classes that can be defined in a language and the classes that can be recognized by a machine, and asks when are they the same classes. So those are the three chapters that I'll be talking about. This intersection, the intersection of these three sets, is actually fairly well developed in graph theory. So for many years, decades now, you have people like Bruno Courcelle and Martin Grohe and Detlef Sisa who have been thinking about graphs, computing machines, and formal logical languages, properties of graphs that can be expressed in a particular logical language. But when you think about matroids and hypergraphs, there isn't nearly as much work done in this intersection. In fact, there are only a couple of papers that you can, maybe 2 or 3 papers that you can say belong in this intersection when you're in the world of matroid theory, and most, I think all of them involve Peter Heleni. So I was looking at one of those papers the other day, and I found a paragraph that I think is quite accurate. So we do not have any good answer to these questions, not even a plausible conjecture, since we are only at the start of an exciting research area. Indeed, we do not expect easy answers here, since the questions combine the difficult area of structural matroid theory with fundamental problems of logic. And I agree with everything in this paragraph. We do not have any good answers yet, and we shouldn't expect good, clean answers for reasons that I will talk about later on. I haven't said what questions they're talking about in this paragraph, but I will do that later on. I'll sort of reveal it. But I also agree that this is a new and exciting research area. It's still a new and exciting research area, even though they wrote these words nearly 15 years ago. The area is still new. Not much work has been done in the intervening time. Okay, so those are the things that I want to talk about. Matroids, graphs, hypergraphs, decidability, computability, complexity theory, and descriptive complexity. This will be sort of a survey talk. I will be talking a lot about unsolved problems, open problems, and conjectures. And I'll be talking quite a lot about work in progress as well. So, and I'm not sure what the background of this audience is, so I may end up explaining things that everybody knows, so apologies in advance. If I'm talking about something and I haven't explained what it is, then please feel free to put up your hand and ask me to explain myself. Okay, so let's carry on. We'll start with complexity theory. So the study of computational problems that are tractable versus computational problems that are intractable. And the fundamental theorem that I want to talk about is Courcelle's theorem. And Courcelle's theorem says that if I take any sentence in the monadic second-order logic of graphs, then I can test whether a graph satisfies that sentence in polynomial time, as long as I restrict my input to graphs that have bounded tree width. So I've highlighted a couple of terms in this theorem that I'm going to explain in a little more depth. I'll start by talking about tree width. I'm not actually really going to explain tree width. I'm sure many of you here know exactly what tree width is. And if you don't, all I'm going to do is draw a picture. And here is that picture. Okay, so the graph on the left has high tree width, graph on the right has low tree width, and that's pretty much all you need to know, right? So, tree width just measures how tree-like a graph is. Okay, so if you have low tree width, you're closer to being tree. If you have tree width 1, you are a tree, or at least a forest. If a class of graphs has got bounded tree width, it means that all the graphs in that class look like trees in some qualitative sense. So that means that if you step back far enough, then the graphs in that class all look like trees. Okay, so a class of graphs with bounded tree width is qualitatively like a class of trees. Okay, so that's tree width. I'm not going to say much more about that. I'll talk about monadic second-order logic for graphs, though. So this is the logical language for graphs, where you have the following ingredients. You've got variables that represent vertices of the graph. You've got variables that represent edges of the graph. And you've got variables that represent sets of variables and sets of edges. And then you need to be able to say things about these variables. So you have these predicates that allow you to talk about when two variables are equal, or when one vertex is contained in a set of vertices, or when one set is contained in another set. We're talking about graphs, so we have to be able to talk about things in a graph-like way, and we'll do that with this binary predicate here, the incidence predicate. So that will let us say when a vertex is incident with an edge. Okay, and then you have standard logical connectives, and, or, not implies equivalence, as well as the standard quantifiers, the existential quantifier and the universal quantifier. So I'll give you an idea of the expressive power of this language by just putting up a sentence in this language. And maybe you want to take a look at this sentence and have a think about what the sentence is actually saying. Or maybe you want to tell us. Right, exactly. So this sentence is saying there is a set of edges such that every vertex v1 is incident with one of the edges in the set. And furthermore, if there is an edge in the set that is incident with v1, then it's the same as the first edge we talked about. So there is a unique edge in the set that is incident with that vertex. So this is expressing the idea that the graph has a perfect matching. Okay, so we've learned something about the expressive power of this logical language. It can express when a graph has a perfect matching. It can also express other familiar graph properties like Hamiltonicity. You might want to think about how would you use this logical language to express the fact that a graph has a Hamiltonian cycle. Or maybe it has three colorable. So this is what makes Courcelle's theorem interesting, right? Because those properties, Hamiltonian, for example, or three colorability, those properties can be expressed in monadic second-order logic, which means that Courcelle's theorem tells us that there is a polynomial time for testing those properties. Now that's surprising, because in general, testing a graph to see whether it's Hamiltonian is an NP-complete problem. So it's an intractable problem. Same with three colorability and other properties as well. So the surprise of Courcelle's theorem is that properties such as those hard properties, those intractable properties that can be expressed in this language, they become tractable when you restrict the structural complexity of your input. So that's what makes Courcelle's theorem interesting. Okay, so this is a very influential meta-theorem in complexity theory. And of course, Matroid theorists are jealous, so they want a version for themselves. So what I'll talk about next is a version of this theorem for matroids. But I'm not going to assume that everybody here knows what a matroid is, so I'll spend a little bit of time talking about matroids. Yes, go ahead. Yep. A property, yeah, sure. Here's an example. Has a non-trivial non-trivial automorphism. Okay, that cannot be expressed in the language. That's the best example I have. There are other NP-complete problems that can't be expressed in the language. Yeah. Mm-hmm.
There are other
Sure. Yes. In fact, I think the most natural version of width for Courcelle's theorem is not tree width but clique width. I think some years after he published this theorem, he or somebody else, I can't remember, strengthened it to classes with bounded clique width, which is another notion of width. So yes, there are many notions of width for which Courcelle's theorem will work. And in fact, we'll be seeing some more of them later. Okay, so what is a matroid? Well, I'm going to put up a definition and I do not want you to read it. Okay, so nobody read this slide. Some people here know exactly what a matroid is, and if so, then you don't need to read this definition. But if you've never seen the definition of a matroid before, well, now's not the time to start learning. This definition is not actually going to help you very much in the remainder of the talk. So I'll just give you a couple of key points. The point is that a matroid is a hypergraph. Okay, so in a hypergraph, I have a finite set, which I will denote with E, and I'll call it the ground set. And I have a collection of subsets. So I will call those subsets hyperedges or independent subsets, depending on the context. So every matroid is a hypergraph, and the point is that the independent subsets of that hypergraph have to obey three rules. They have to obey these three axioms, but what these axioms say is not especially important for this talk. So instead of talking more about this definition, I'll just give you an example. So let F be a field, let V be a vector space over that field, and let your ground set be a finite subset of those vectors. Okay, so take a finite set of vectors from a vector space, and let the independent subsets be the subsets that are linearly independent in the vector space. And that's a matroid. That is an example of a matroid. So any matroid that arises in that way, I'll say is representable over that field, or it's F representable. Okay, so any questions about matroids before we move on? Okay, so with this definition, I can now talk about our matroid version of Courcelle's theorem. So this was proved by Peter-Heleni in 2006. So take any sentence you like in the monadic second-order logic of matroids. Then there is a polynomial time algorithm for testing whether a matroid satisfies that sentence. And the algorithm runs a polynomial time as long as you restrict your input to a class of matroids that are representable over a particular finite field, and the class has bounded branch width. And I won't really say anything about what branch width is. It's just think of it as being like a matroid version of tree width, and that's a good enough picture for what branch width means. And I will note that the field has to be finite, because if it's infinite, then testing a sentence in this monadic second-order logic may be NP-complete, even when I restrict the branch width. Okay, so finite fields are necessary for this theorem to work. And in fact, that reflects quite a lot of matroid theory. We find that matroids representable over finite fields have good structure theories, a little bit like the Robertson-Seymour style structure theories for classes of graphs. Once you move to infinite fields, everything falls apart.
Does this contain Courcelle's theorem?
Yes, it does. Yeah. It takes a little bit of work. It's not completely obvious. Maybe you have to do a page of work. Okay, so what else am I going to do? I will just illustrate how the monadic second-order logic for matroids differs from monadic second-order logic for graphs. It's almost the same. You've got variables that represent elements of the ground set, and you have variables that represent subsets of the ground set. And you don't no longer talk about incidence of a vertex and an edge because there are no vertices. Instead, you have a unary predicate which allows you to talk about a subset being independent. Okay, so an example of a sentence in this language might look something like this. This is saying that every subset of an independent set is itself independent. Right? And that happens to be one of the axioms for matroids. Okay, so when we started this project maybe 3 or 4 years ago, what we really wanted to do was to understand why Heleni's theorem worked. And we were led to this definition here. It's a little bit technical. So I'll illustrate it with a picture on the next page. So imagine that you've got a hypergraph and you have partitioned the ground set into 2 sets U and V. I'm going to define an equivalence relation on subsets of U. So take X and X prime, subsets of U. And I will say that they are equivalent if V can't tell them apart. So V cannot distinguish between X and X prime. So what I mean by that is, if you take any subset Z of V, then X union Z and X prime union Z are both hyperedges, or neither one is a hyperedge. Okay? So I'll illustrate this definition with a picture. Here is my hypergraph. So the dots are the elements of the ground set. The circles and the ellipses, those are hyperedges. There's no particular structure to this hyperedge. It's not a matroid or anything. It's just a completely arbitrary hypergraph. The partition is the vertical bar down the middle, so I have U on the left, and I've colored in 2 subsets of U. So I have the blue subset and the orange subset. So can you tell me whether the blue and the orange are equivalent or inequivalent? Can V tell the difference between the orange set and the blue set? Yes, right, everybody's reached there? So if I color in, if I make Z equal to that set of 3 red edges, then I see that orange union red is a hyperedge, but blue union red is not a hyperedge. Okay, so V is able to distinguish between blue and orange. So blue and orange are inequivalent subsets in this hyperedge, inequivalent subsets of U. Okay, everybody happy with that definition? Okay, so now we're led to the notion of a decomposition tree for a hyperedge, for a hypergraph. So a decomposition tree will be familiar to those of you who have worked with branch width before. It's a tree where every internal node has got degree 3. And the leaves of the tree are in bijection with the ground set of my hypergraph. Okay, and I think of this tree as displaying certain subsets. So a displayed set is one that I get by deleting an edge of the tree and looking at the 2 components and taking the leaves in one of those components. Okay, so that blue set is displayed by this edge, and so is the orange set. Okay, so here's the end of the sequence of technical definitions. If I have a hypergraph and a decomposition tree like this, and whenever U is a displayed set in the decomposition, then the number of equivalence classes amongst the subsets of U is at most k, then I'll say that this hypergraph has got decomposition width at most k. Okay, so this decomposition tree is telling me that the width of this hypergraph is at most k. The decomposition width is at most k. So after we came up with this definition, we realized a little bit later that it's equivalent to a definition that was used by Dan Crowell, although our definition looks quite different from the definition given by Dan. So that was a little bit unsettling. But then we realized that we our work didn't completely duplicate Dan's work, so we had done some stuff that Dan had not, so that was a relief. But anyway, this terminology, decomposition width, is due to Dan Crowell. He came up with that terminology. Okay, so the point of having a decomposition tree with this kind of bound is that, well, if you have a class of hypergraphs and they all have decomposition width at most k, then you can process those hypergraphs using tree automaton. A tree automaton that uses at most k states, at most k colors. And in particular, you can use a tree automaton to test any sentence you like in the monadic second order of logic. So that's why this notion is sort of central to the workings of Heleni's theorem. So I'll explain what a tree automaton does. So in a tree automaton, you've got a finite set of states, or a finite set of colors. I think of every state as being a color. And a tree automaton is just a simple computer that is going to process input and produce output. So you start by applying colors to the leaves of the tree. And I think of this assignment of colors as being the input to the computation. And so the computation proceeds as follows. You let the colors move towards the center of the tree, like that. And now when two colors have met, when they've run into each other at a node like this, they will blend. The colors will blend to form a third color. Like so. So every one of the internal nodes has got a set of blending rules attached to it. So when two colors meet at one of those internal nodes, they get blended to form a different color according to the rules at that location. And then you continue on. So when two nodes have merged into a blended node, that blended node continues moving towards the center of the tree. And we just repeat. So when two colors have met, they blend together to give a different color. And we just continue until there is only one colored node left. There is only one color left. And that color is the output of the computation. Okay, so the input is a coloring of the leaves. The output is a color attached to the final node at the end of this computation. So I think of the tree as either accepting the input or rejecting the input, depending on what this color is. If green stands for accepting, then it just accepted that input. Okay? So the point is that if you have a class of hypergraphs with bounded decomposition width, then that means that there is an automaton which can test any sentence you like in the logic. And these automata are fast, right? Because there's no backtracking. They just process all the colors from the leaves towards the center of the tree. And that's why you end up with a polynomial time algorithm. So you summarize that with this theorem here, which also follows from work of Dan Crowell. Imagine that you have a class of hypergraphs and that it has bounded decomposition width, and what is more, you can produce one of those decomposition trees in polynomial time. Then, if you take any sentence that you like in the monadic second order logic of hypergraphs, you can test it in polynomial time. So you simply create that decomposition tree and you run the appropriate automaton on it, and there's your answer. Okay, so that's why Heleni's theorem works. So this is sort of the abstract theorem that lies underneath Heleni's theorem. And we were able to use it to extend Heleni's theorem to other classes of matroids. The question is, how do you produce that decomposition tree in polynomial time? That's not obvious, but fortunately we've got an algorithm due to Sang-Il and to Paul Seymour, which can produce a branch with decomposition. We're able to use that for at least some classes of matroids. So now we can test any sentence in polynomial time when I have a class of matroids with bounded branch width that is a subclass of one of these four subclasses. I'm not really going to say much about what these subclasses are. I mean, some of us have been talking about bicircular matroids all afternoon, so you'll recognize that. I won't say anything about these. I will say something about game graphic matroids because they're an important class that we're going to see a few times later on in the afternoon. So in a game graphic situation, you have a group called the group H. For this explanation, I'll just assume that H is abelian, but everything goes through without too much difficulty for non-abelian groups. You can assume H is any group. And you have a graph, and you have labeled the edges of the graph with elements from the group. Okay, so in this particular case, I've got the cyclic group of size 3. I've labeled every edge with an element from that cyclic group. And that allows me to distinguish between cycles of the graph. So if when I go around the edges in a cycle and I sum the labels together, if in that case I get the identity of the group, I'll call it a balanced cycle. So this red cycle is an example of a balanced cycle. The sum of edges is equal to the identity. Any other cycle is unbalanced. So this blue cycle is unbalanced because when I sum around the edges, I do not get the identity. Okay? Under these circumstances, I have a matroid. Okay, so the ground set of the matroid is the set of edges in the graph. And what are the independent sets of the matroid? Well, they look like this. So every component can contain no more than one cycle. So you'll notice that in this blue subgraph, every component has at most one cycle. And what's more, that cycle must be unbalanced. Okay, so it does not sum up to the identity. Okay, and that turns out to be a matroid. So I take the ground set as the set of edges. The independent sets are the subsets of edges with this property. No balanced cycles, and at most one cycle per component. So that's a matroid, and any matroid that arises in that way, I say, is game graphic. It's H game graphic. And H game graphic matroids are really important. They are kind of like analogues for matroids representable over fields. So you have matroids representable over fields, and these are like matroids representable over groups. And the matroids that arise in this way are analogous to matroids representable over fields in many ways. So you have this very extensive work by Jim Gielen, Bert Ararts, Jeff Whittle, which is sort of like a matroid analog for Robertson and Seymour style graph minors theorems. And in that work by these three authors, the matroids that are H game graphic for a finite group H, those matroids keep on arising. So these form a fundamental class.
Are there any restrictions on the graph, or?
Nope, any graph you like. Okay, so that's all I want to say in the first chapter. I'm going to move on to the next chapter. So this is probably a good time to just pause and see if there are any more questions or comments.
If you restrict this theorem to game graphic matrix,
Right.
is there a chance that the original Courcelle theorem may imply
The which theorem?
the
Courcelle's theorem. Yes, because if you have the trivial group, then you just get graphs. Yeah.
The Courcelle theorem for graphs
Yes.
will allow, it can also label.
Oh, decorate it. Sure. Well, it's a slightly different language because in Courcelle's theorem, you're talking about you have incidence between vertices and graphs. In our matroid language, you have a different type of predicate which takes as input a subset of edges and determines whether it's independent or not. So I think the answer to your question is I'm not sure. If the answer is yes, then I don't think it's obvious. I'll just say that. Yeah, I don't know for sure. You won't see any connection between these pictures and the chapter titles, by the way. These are just pictures that I took while I was hiking around New Zealand that I thought were nice, so I put them up. That's all. Are there any other questions or comments? Okay, so let's now talk about decidability. So in decidability, you're asking whether there is a theorem testing machine. So it's about the interaction between a class of objects and a language that talks about those objects. So you have a class of mathematical objects, you have a language that talks about them, and you ask the question, is there a Turing machine which can take as input any sentence in the language and then decide whether it's a theorem or not? So whether that sentence holds for every object in the class, or whether there is a counterexample. Okay, so if there is such a Turing machine, if there is a finite procedure which will take any sentence and test to see whether it's a theorem, you say that the class has a decidable theory. Otherwise, it has an undecidable theory. And this is a very natural and important division between simple behavior. Decidability sort of means you've got simple behavior, and undecidability means you've got complex behavior. And so over the course of the last century, many of the big names in logic have made contributions to the study of decidability, so Lowenheim and Pressburger and Skolin and Tarski and so forth. So in the context of graphs, and in particular minor closed class of graphs, the foundational theorem here is due to Detlef. And it's a really beautiful theorem. I love this theorem a great deal. Take a minor closed class of graphs and think about the monadic second order logic for graphs. That class has a decidable monadic second order theory if and only if it has bounded tree width. So this is a really beautiful interaction between what machines are capable of deciding, what languages are capable of expressing, and the structure of discrete objects. So one direction of this theorem is essentially due to Courcelle's theorem. So if you have bounded tree width, then the class can be processed by a tree automaton. In particular, for every sentence, there is a tree automaton that can process the graphs and decide whether the sentence holds. And once you have that, decidability follows without too much difficulty. So you construct the sentence that says, is there a counterexample to this theorem? That is now a monadic sentence. And you look at the automaton, the tree automaton for that sentence, and there is a finite procedure to decide whether that automaton will ever be satisfied by a counterexample. Okay, so that was quite a quick explanation. The point is that once you can be processed by a tree automaton, decidability follows quite quickly. Okay, so once you have Courcelle's theorem, decidability follows quickly. The other direction is hard and relies on the deep structure theorems of Robertson and Seymour. So the important point here is that basically it appears that if you have a decidable theory, then in some sense you are tree-like. If the class has a decidable theory, then it is in some sense tree-like. In order to prove that it is undecidable, you need to be able to talk about grids. Okay, so I'll say a little bit about why that appears to be the case. Well, I've sort of given one explanation. If you are tree-like, then you can be processed by tree automata, and decidability follows relatively quickly from that. So trees lead to decidability, and it appears that in some sense that's the only way that you get decidability. In fact, Caesar has conjectured that if you have decidable theory, then in some sense your class of objects is vaguely tree-like. There are many technicalities in that conjecture, so I won't go into it, but it appears that trees are somehow synonymous with decidability. Now, why are grids important for undecidability? Well, a grid looks a little bit like a Turing machine, or rather a Turing machine evolving through time. So if you can talk about a grid in your logical language, then it may be that you can encode the state of a Turing machine in a row of your grid. So you can use your language to encode the symbols on the tape of a Turing machine into this row of the grid. And then what you do is you use your language to talk about the next row being the next state of the Turing machine after one step of time. So what we've got here is an encoding of the evolution of a Turing machine as it goes through its computation. So you may be able to talk about the way that the Turing machine computes. So if you're able to talk about a grid, then you're able to talk about arbitrary Turing machines and how they compute. And that means you can start talking about undecidable things. You can start talking about, whether this Turing machine will ever halt on a particular input. Okay, and we know that there can't be a finite procedure for solving that problem. That's the halting problem. That's the first, one of the first ever undecidable problems. Okay, so if you can encode a grid, then you may be able to encode computation of Turing machines, which means you can encode undecidable problems, which means you have an undecidable theory. Okay, so that's why we have this sort of dichotomy between decidability in trees on one side and undecidability on grids on the other. Now, what's really beautiful is that, of course, this is exactly the same dichotomy that you get from the Robertson-Seymour theory of graph classes, minor closed classes of graphs. Robertson-Seymour say, take any minor closed class of graphs, either it has bounded tree width, so it looks a bit like this, or it contains arbitrarily big grid minors. So you have the same dichotomy appearing in structure theory of graphs and in the dichotomy between decidability and undecidability. I think that's incredibly beautiful. I don't think there is any superficial reason to believe that these same problems should exhibit exactly the same dichotomy. So that's one of the reasons I like Caesar's theorem so much. Okay, so this is all very nice. What about matroids? What can we say? What can we ask similar questions about matroids? Well, yes, we can ask them, just don't expect an answer. So the obvious thing to do is to look at minor closed classes of matroids and characterize which ones have decidable monadic second order theories. This is not going to have a nice clean answer like Caesar's theorem. That's not realistic. And in fact, it's this problem that Helene and Caesar were talking about in that paragraph that I put up at the beginning of the talk. They were saying we should not expect any good answers, and that's correct. Why should we not expect good answers? Well, because I think to get a good answer to this, you would need a structure theorem that covers all minor closed classes of matroids. And there just can't be such a theorem. It's not like graphs. So the Robertson and Seymour theorems cover all minor closed classes of graphs. And we cannot expect that for minor closed classes of matroids in general. So this is going to be extremely difficult. And when I say extremely difficult, I think I mean impossible. I just don't think there can be a clean answer to this question. But that doesn't mean that we can't ask interesting questions about it. So we have some partial answers. So Helene and Caesar in their paper, they gave an analog of Caesar's theorem when we restrict to matroids representable over a finite field. So choose any finite field you like, take a minor closed class of matroids that are representable over that field. That will have a decidable monadic second order theory if and only if it has bounded branch width. So Caesar's theorem goes through to matroids representable over finite fields. And this is another example of theorems for graphs working in matroids as long as we restrict to finite field representable. And it's not too difficult to see that, again, things turn bad if we are instead looking at infinite fields. So if you have a class of matroids representable over the class of matroids representable over an infinite field, that will have an undecidable theory, even if we restrict to rank 3. I haven't said what rank is, but it just means the largest independent set. And if you have rank 3, then you've got bounded branch width. So this theorem just fails for infinite fields. Okay, are there any questions at this point? So we might ask, well, what are there other classes to which we can extend this? Okay. Yes, yes. So just take all, rank 3 and less is a minor closed class. Yeah. So take all matroids, all real representable matroids, say of rank at most 3. That is a minor closed class. It has branch width at most 3. And it basically contains all the complexity of graphs. So it certainly has an undecidable theory. Okay, so can we extend this further? Yes, we can. So this is just saying that the same works when for gain graphic matroids, where your gain graphic over a finite group. So choose your finite group H. Consider a minor closed class of matroids that are gain graphic over that group. That class of matroids will have a decidable theory if and only if it has bounded branch width. I haven't called this a theorem yet because nothing is written down, but this should be relatively straightforward. Like the strategy is clear. So this is not a written down theorem yet, but I don't anticipate any difficulties in finishing this theorem off. And it's also, you can do a little bit of work and you can see that if H is an infinite group, then you'll have an undecidable theory. So again, we sort of see this dichotomy between finite and infinite in both fields and groups. So you have good behavior over finite fields and finite groups, and you have complicated behavior over infinite fields and infinite groups. The most straightforward analog of Caesar's theorem for matroids would be just to say, take any minor closed class of matroids, just a general minor closed class of matroids. It has a decidable theory if and only if it has bounded branch width. So is that true? Well, here's one direction. This tells you that it's not true because you can have bounded branch width and still have an undecidable theory. What about the other direction? Can you have a decidable theory and unbounded branch width? Yes, you can do that as well. So this is work in progress with me and Nathan Balla and Mike Newman. So take the class of uniform matroids. That's got a decidable theory, so there is a theorem testing machine for uniform matroids, but it certainly has unbounded branch width. So Caesar's theorem for general classes of matroids fails in both directions. Okay, so the picture for matroids is going to be a lot more complicated. And I think that's all I wanted to say about decidability. So we can just pause and take a look at the photo and ask if there are any questions here. Any questions or comments? Okay, so if you're happy for me to move on, then we'll start talking about descriptive complexity. And the idea of descriptive complexity fundamentally is to talk about, to try and prove equivalence of definability and recognizability. So definability refers to a language. If I have a language, then what classes can be defined by that language? So the class of Hamiltonian graphs, that's definable in a monadic second order language. The class of graphs with a non-trivial automorphism, that is not definable. Okay? Recognizability refers to a machine. So given a class of graphs, is there a machine, given a particular type of machine, is there a class? Given a particular class of machines, can those machines capture a particular class? So the class of, if I think about polynomial time Turing machines, they cannot recognize the class of Hamiltonian graphs, well, assuming P is not equal to NP. Okay, and in descriptive complexity, we're basically trying to show that those classes coincide. So a class of objects is definable in the language if and only if it is recognizable by a machine. Okay, so maybe this will become clearer if I just talk about one of the sort of founding examples, which is Bucchi's theorem. Bucchi's theorem talks about the universe of binary strings. So we have a language, a monadic second order language for binary strings, and we have a set of machines which process binary strings, finite state automata. Bucchi's theorem says that a set of strings is definable in the language if and only if it is recognizable by one of the machines. So this is sort of a canonical example of the sort of theorem I'm going to talk about. So first of all, what is the monadic second order logic for strings? Well, our variables now represent positions in the strings. So we also have variables representing sets of positions. And then what else do we have? I have a predicate allowing me to say that there is a 0 in this position, another predicate that allows me to say there is a 1 in this position, and a binary predicate that allows me to say this position is a successor to this position. So this position comes immediately after that. So for example, I can write things like this. So this sentence is saying that every 0 should be followed by a 1. And every 1 should be followed by a 0. Okay, so this sentence characterizes alternating strings. So in one direction of Bookie's theorem, you're saying that for every such sentence, there is a corresponding finite state automaton. And a finite state automaton is basically something, a directed graph like this. So the automaton is going to start at the start vertex, and it's going to process the string character by character. And as it moves from character to character, it's going to move around this directed graph, just following the directions on the arrows. So if it's reading a 0, it will move along the 0 arrow. If it's reading a 1, it will move along the 1 arrow. And you can see that this machine is going to terminate its computation in one of these two accepting states if and only if the string is alternating. Okay, so this machine accepts exactly the same strings that this sentence characterizes. So this machine recognizes exactly the same strings that are defined by this sentence. So one direction of Bookie's theorem says that if a set of strings is definable in the language, then it can be recognized by a finite state automaton. That's probably the easier direction of Bookie's theorem. The other direction says that if there is a finite state automaton that accepts binary strings, then there is a sentence that defines the strings that are accepted by the machine. So I'll just give you a brief rundown of how that proof works. So imagine that you've got a machine, and this is the set of states. The states are just the nodes in the directed graph. So you've got states Q1 up to Qt. Here's how you construct the sentence that defines the strings that are recognized by the machine. So you say, first of all, there exists a partition of all the positions into T different sets. And I think of those T different sets as corresponding to the T states of the machine, the T nodes of the machine. So if a position is in block number I in this partition, that reflects the fact that as the machine processes the string, it will be in state number I after reading that character. Okay, so what the partition does is tells me what state will the machine be in after reading each position. Okay, so that's the core idea. The rest of it is relatively straightforward. I just need to say the first position in the string is in the block of the partition that corresponds to the starting state, and the final position of the string is in the block of the partition that corresponds to one of the accepting states. And then I need to have this complicated thing that says that all the transitions of the machine are respected. So if I'm in this position here, and the partition is telling me that I am in state I after reading this character, and I'm reading a 0 here, and I should transition to state J, the machine tells me that I should transition to state J, then the sentence should say, well, if there's a 0 in this position, and this position is in block number I, then the next position, the successor position, that should be in block number J. Okay, so you can encode the workings of the machine in that sort of way, in a sentence in that way. So you get to build a sentence which encodes the working of the machine. So that's how you prove Bookie's theorem. For every sentence, there is a machine which recognizes exactly the strings that are defined by the sentence, and vice versa. So it's a really nice theorem, and the ideas behind it are quite, you find them in all this sort of descriptive complexity. So here's a conjecture that Courcelle made, and he's really conjecturing a converse to his to his theorem. So Courcelle's theorem says, amongst other things, that if you have a sentence in the monadic second order logic of graphs, then, and our universe is the graphs with bounded tree width at most k, say, then there is a tree automaton which will process all trees with tree width at most k, and it will accept exactly the trees which satisfy that sentence. Courcelle is conjecturing here the converse of that. So your universe is the set of graphs with tree width at most k. If there is a tree, take a tree automaton and look at the set of trees that are accepted by that automaton. That class of graphs, the class of graphs that are accepted by that tree automaton, should be definable in the language. That's what Courcelle is conjecturing. This is really hard. If we could talk about, the decomposition tree in our language, then we could do the same sort of trick that we did in Bookie's theorem. We could partition up the nodes of that tree according to the states of the automaton and so forth and so forth. There's a trick that you can use as long as you can talk about the decomposition tree. But that's the hard part. So talking about the decomposition tree in the logic of these graphs. And this went unsolved for quite a long time until it was recently resolved by these two Polish mathematicians. I'll try their names. Bojanczyk, Pilipczuk. I mean, I would love to be told if I'm doing that right. Please feel free to correct me. Anyway, so this is hard. What about matroid analogues for this conjecture? Well, the obvious conjecture is false. So take a class of hypergraphs, let's say, with bounded decomposition width. If you've got bounded decomposition width, that means that you can talk about processing these hypergraphs with a machine, or with machines. So you could say that if, for any given machine, you look at the hypergraphs in our universe that are accepted by that machine, and that class of hypergraphs should be definable in the language. But this is false, because the language of hypergraphs is slightly weaker than the language of graphs. In the language of graphs, you're allowed to talk about sets of edges. But in the language of hypergraphs, you're not allowed to talk about sets of hyperedges. And that comparative weakness makes a big difference. It makes this conjecture false. But I wonder whether this conjecture could be true. I don't see how to come up with counterexamples to this conjecture within the class of matroids that are representable over the field of size 2. Maybe there is a trick. I'm not sure that I really believe this conjecture, but I don't yet have a counterexample. And I'll just note that counting monadic second-order logic I haven't defined, but it's basically just the same as monadic second-order logic, except that you've got predicates that say things like this set of vertices has cardinality 1 mod 5, or 10 mod 17, or a billion mod a trillion, or something like that. You give yourself all of those predicates. So you just extend your language a little bit. Counting modulo 10 or 17 or a billion, that's something that the automata can do. So in order for the converse to Courcelle's conjecture to hold, you need to include that sort of thing in your language. Okay, I've come to the end of what I wanted to say. So thank you very much for your attention.